Exercise 52 show there is an isomorphism of vector spaces from the exterior power of the due of vector space to the due of the exterior power of vector space, which means, let me write that. So let's suppose it. K is some integer, y is some vector space. Let's take its due. Show that we have isomorphism in this with finite dimensional vector space, let's say over R. So the solution is that we can construct a pairing. So I will explain later why I'm interested in this. This explains phenomena of the sub-exercise of exercise 51 in the last video. So let's first construct a pairing. Construct a pairing by define the map on the generating elements or elementary elements generating it, and then expand by linearity. So let's say if you have f1 fk, and then here let's say you have v1 vk, then let's map it to the determinant or the fi with j, ij bigger or equal than 1 less equal than k. So this is a k by k matrix. Compute the determinant and show this is non-degenerate. This is bilinear and non-degenerate. Hence, a perfect pairing. Instead of proving this, so let's just see how this explains the following phenomena. So recall we have a sub-exercise which tells that in the case of, so we're talking about 2 or 2 star, which we mean, what we really mean is this, okay, claiming that it has a basis given by the determinant. So basis is given by, so let's first see, it's defined to be bilinear alternating map from R2 Cartesian product to R, and we claim that a basis is given by v1, v2, map to x dxi, I here is 1, 2, evaluating on 1 with 2, which by definition given exercise 51, this is a determinant of v1, v2 as a 2 by 2 matrix. The question is, or the phenomenon is, we know that a basis in general by our this construction, so in general a basis is given by M1, okay, and then sorry, so here we should be more precise. So suppose this is dimension D, or finitely generated by D elements. So M1, MD as R algebra, as R module, finitely generated R module. This is the most general case. And then this, a basis of this, here I mean tensor product. The basis of this is given by mi1, mi2, mik, where this i1, i2, ik comes from an increasing sequence of integers, and actually we denote for that generate. This is generating set, which means this is span of this. Not only span of this, I really mean this is the basis of it. Okay, and we denote this by wedge. So in particular, in this example, precise example, we would say that gamma 2 R2 star should, so here which means M is the U space of R2 should be have a basis of, because R2 we have a basis E1, E2 standard basis, so this should have its basis E1 wedge E2. It's one dimensional, right? And more precisely, it's not this, but generating set of M, generating set of due space, which means U1 due, E2 due, where E1 due is the map that's such that acting on EJ equals 1 if J equals 1, 0, that equals 1. Or put more directly, EI star acting on EJ equals delta IJ. Right, and then if you use this, then we would feel that, okay, so this should be a basis, right? But look at what is the basis here. The basis here is given by the determinant, while so the determinant maps v1, v2, so the determinant of v1, v2, putting out the column matrix, noticing that this is actually corresponds to the map of E1 tensor E2 minus E2 tensor E1 as element in I would say E1 star, 2 star, 2 star, and the element in gamma 2 R2 due. Because notice this one maps V1, V2 to what? To, let's put it more precise, but this is X. Let's put it, this is A, B, C, D, then this should be AD minus BC, right? This determinant. And this element maps V1, V2 to, so E1 star V1, E2 star V2 minus E2 star V1, E1 star V2, which is exactly A D minus BC, right? More precisely what I'm sure meaning. And so, in other words, this corresponds to E1 star wedge E2 star minus E2 star wedge E1 star. So in what sense does this match to the well-known fact that this gives you the basis? Although actually, while the are actually collinear, I would say, because we know f wedge j equals minus j wedge f, so actually they're collinear. Wow, but I would like to think directly like this. So actually, I think there is isomorphism, the isomorphism we mentioned about. So basically, what we do is we have this first description of bilinear alternating homomorphism from product of R2 with R2 to R. Secondly, we want to see there is bijection with exterior algebra, exterior power. What really do we do is that, so those alternating bilinear map from R2 to R2, R product R2 to R is bijective with homomorphisms from this by the definition and construction. That's, let me put R linear alternating. That's from the definition, right? Which means that if you want to use this as a definition, as I mentioned in the sub-exercise, so someone use this as a definition, I would say actually what you're doing is you're using, so this is actually this one, right? And the map is, this is your f, then your map to this f tilde. by universal property. This is basically the isomorphism. And because of our exercise, this is isomorphic too. Or to Q. And this have a basis E1 star wedge E2 star. So basically, one would say that indeed this bilinear map, which maps V1, V2 to its determinant, actually corresponds to here, which maps V1 wedge V2 to determinant, really corresponds to this one, and there's isomorphism. So here it doesn't matter. I mean, yes, this is collinear with this. Anyway, this is a one-dimensional vector space. Whatever basis you choose give you the correct dimension. Up to isomorphism, they give you a basis, but I would like to say that this standard basis here really corresponds directly to that determinant, because what is this? This is mapped to, following our notation as where we started. Solution here, call it phi. So this is telling us you have constructed a map from here to the due of it mapping f1 wedge fk to phi of f1 wedge fk, and left the second position blank, right? Which means determinant of fi ij. This is an isomorphism. So which means indeed this is mapped to determinant of ei. And so when you put in your this is indeed the map that maps V1, V2 to determinant of E1, V1, E1, V2. So let me just write it more. So that determinant of EI star J, this is phi of U1 star wedge E2 star. And this is the image of U1 star wedge E2 star. And there this isomorphism of from wedge to it's from wedge of due to the due of wedge. And this one as due of wedge maps a vector to a real number, which is determinant of E1, V1, E1, V2, E2, V1, E2, V2. And this is exactly telling you that if this is AB, this is CD, then this is the determinant of A. B. So, which means better I should how do we construct this? I and j, probably I should here the row I use I, yeah, I use it correctly, so the row is I, which means here actually anyway, you could always modify the order. Let me just keep this, so it doesn't matter. E1 V1, E1 V2, AB. So E2 V1, E2 V2. Still give you AD minus BC, which corresponds to this description. So I would say this description actually comes from applying that pairing, that isomorphism between the exterior of dual and dual exterior. And so what I want to say that this is really the same as this one, which means if you start here and then enter the isomorphism, you map to this determinant of EI star, which is the F tilde, and it corresponds to the F, which is exactly the determinant map, and tells, or it's clarified or justifies why one would sometimes say that this is directly to be the bilinear alternating maps whose basis is given by determinant. And as you could say this similar reasoning, and suppose you know the standard basis is given by set. Where did I wrote that? Yes, here. You know this. Then you could imagine that you could give a description of basis for the vector space of, if it's in there under the setting of vector space. So that would be bilinear or multilinear maps from the product of M to R that is alternating, and a basis would be given again by V1, V2. So I suppose this is K times Vk, and this should be mapped to, again, the determinant of a matrix, and here you got your EI1 star with 1, etc. EI2 star with 1, the second row, etc. And the last row is EIK star with K, etc. So what you're doing is exactly you're cutting out I1's row, the I2's row, until the IK's row of the matrix. V1, V2, Vk, right? You're cutting out those I1, I2, Ik, and compute the determinant. This is exactly the basis we described before the sub exercise. So this explains this. strange phenomena, which is very nice.